Hello everybody, we're talking about graphing polynomials now. This first set, we're talking about identifying curves. Looking at this table of values, what you want to do is compare the rates of change. So how is this changing each time? So let's see, we're adding, I think it's 64, and then here it's adding 128, and here it's adding 256. And really, when we jump into polynomials now, we want to compare how is it changing on the second level. So how is this changing? So this is going up by 64 and 128, and then you can see that this one it's changing by the same rate over and over again. This is an exponential type. So this is doubling. It looks like it's doubling each time. But if it's changing from step to step the same, and you can carry that out, then this is an exponential. So let's compare this one. So 49 and 36, that's 13. And then 49 and 64, that's 15. And then 64 and 81. That's 17. So it's not a constant rate of change, but then when I go up my second level, it looks like it's changing by 2 and by 2. So the second level out, it is a constant rate of change. So this is what we call a polynomial. So polynomial. And it's actually a quadratic because if it's the second level out, then it's an x squared type of thing. So actually that's what it is, isn't it? X squared. Now this one, if I compare the rates of change, so it's changing by 2 and by 2 and by 2. So it's a constant rate of change, so this is linear. So polynomial, you see that the rates of change are going more towards a constant. Linear, it's right at a constant. Exponential, it actually stays the same. Like the change between the changes stays the same. So in calculus, you'll understand this a lot better. But as you go out, the changes are still the changes in exponential. In polynomials, they work towards getting to a constant rate of change, and even then the change is 0, right? And linear, the change is 0. So that's what we call a constant rate of change for the linear. Okay, so all you have to do is compare those rates of change, and then you can tell what type it is, the characteristics, and maybe you can even write the equation. So this one looks like it's starting at, well, maybe it's 2 to the 6th. Is that right? So 2x, 2 to the x power. I think that's right. And then, so let me just check that. So 2 to the 6th power is 64, and 2 to the 7th is 128, I think. So put that on your calculator, just check. The polynomial looks like it's x squared. And the linear equation, so we'd want to march back to what is my starting position, but 2 times x, and let's see, to make it work, 2 times x will be 12, so it looks like I'm taking away 1. So 2x minus 1. So that's how I do those. Now we talk about graphing from the table above. So you can take that equation, y equals 2 to the x. So, or 2 to the x, not 2x. So when it's 0, it's equal to 1. When it's 1, it's equal to 2. When it's 2, it's equal to 4. So the exponential, so 3. 2 to the 3rd power is 8. So it jumps up to here. And 2 to the 4th is 16. So it jumps way off the page. So it's going up like this. So that's how you'd graph an exponential. Graphing x squared. Well, you can start anywhere you want, but let's do this. So 0 squared is just there, 1 squared is there, negative 1 squared is positive 1, 2 squared is 4, and negative 2 squared is also positive 4. So it has a kind of a U shape like this. And then that 2x minus 1. So when x is 0, I get negative 1. When x is 1, I get 2 minus 1, which is 1. And it should have a constant slope, so it should be like this. Okay. So that's how you graph those three different types. And you can pull it right from the list of coordinates on the previous page. Graphs of power functions. So sketch graphs of those described. So x squared has a shape of a u. X to the fourth has a shape of a u, because even powers, they go up on both sides. Or if there's a negative in front, then they're going to both go down. Odd powers, where it's x cubed, will start low and go high. Or x to the fifth would be something maybe like that. And I have these different relative maximums and minimums. Squared, there's 1. Cubed, so this is 2. So there's one less kind of turn for these different ones. So fourth, fifth. So 1 turn, 2 turns. So there's one less than the number of the highest exponent, if that makes sense. So x squared has 1 turn. X cubed has 2 turns. X to the fourth has 3 turns. And x to the fifth has 4 turns. Possible. Okay. So that'll help you out with this. So x cubed and x to the fifth. And x squared and x cubed. So you can just find some values, make a little table of values for your x squared. So this is x squared, and this is x, and this is x cubed. So you could try like -2, -1, 0, and 1, and 2. Try those values and see what you get. And same thing over here. And see what you get. And then you can plot those points on the graph and see how they look. Okay, and then you're going to jump into GeoGebra and do a couple of these graphs. So Q sub n, and I would just use x so that it works in GeoGebra. Try putting that equation in and that equation in on the same graph, and then you can sketch it below here. Okay, and then also finding zeros of functions. So where do they cross the 0 x-axis, right? So put that into GeoGebra and see what happens. And I can tell you that I think it's going to cross at what makes these 0, right? Because if f of x is equal to 0, that's right there, that point. So if f of x is equal to 0, so we have this function, this curve going around, where it crosses the x-axis means that the function is equal to 0 at that point. So look at those values, where it's crossing the x-axis. And that's what it asks you to do right there. Okay. And input that, and so it's mostly just a GeoGebra activity, and then you'll answer these questions in your notebook.